Folks, I decided to make a video today for the homework questions that were posted on the Jamboard, just to save us a bit of time during our synchronous class this afternoon. So I'm looking, I think we've got 3 or 4 questions here from the projections lesson. So this first one is 8A, and it says determine the scalar and vector projections of A, vector A, onto each of the 3 axes. So I think probably the sticking point was here, not knowing what vector to use. So remember that you've got those I hat, j hat, and k hat vectors that are representative of the x, y, and z axis. So I'm going to find the scalar projection of A onto I hat, and that will be for the x-axis. And then I'm not going to actually do the y and z axis. I'll leave that for you, but it would be the exact same thing, but using the j hat and k hat instead. So we know that the scalar projection is A dot I hat over the magnitude of I hat. So here we've got the scalar projection would be -1 to 4 dot 1 0 0, and the magnitude of I hat, I don't need to calculate it. I know that that's a unit vector with a magnitude of 1. So here we've got -1 times 1 plus 2 times 0, and you'll see what's happening here with the 0 and 0 in the I hat. They just end up canceling those out. So here the vector, or the scalar projection, pardon me, is -1. And notice that's not a coincidence that that's going to be just the x component of vector A. The vector projection of A onto I hat, remember that that is going to be A dot I hat over the magnitude of I hat squared times I hat. So we've got, we know, kind of like looking back on this is -1 when we do A dot I hat over the magnitude of I hat, which is 1 squared, times this vector. So that's -1 times my vector, so it's a scalar multiple of the vector in the direction of the x-axis. So it would be the vector -1 0 0. So you would do for the x, that is for the x-axis. So for the y and z, it would be the same, except using j hat and k hat. So it's going to work out the exact same way, and the values that you get are basically, remember that the projection is how much is this vector helping or working with the x-axis, y-axis, and z-axis. So hopefully that's not a surprise that it's working -1 in the x-axis direction. So you'll get similar values for the y and z. The next one, we have this isosceles triangle where the magnitude of A equals the magnitude of B. So we want to draw the scalar projection of A on C. So I'm just going to pick a different color, maybe green. And remember that our scalar projection is if we drop a 90 degrees, so that this here is the scalar projection of A onto C. If we redraw this diagram, so that was part A. So for B, if I redraw the diagram, there's vector C, and I had A going like that and B going like that. If we relocate B, we want to find the projection of B onto C. So here, remember that vectors have magnitude and they have direction, but they do not have location. So this theta here, this theta here, we would be able to see, that because of the Z pattern there, hopefully you guys can see my highlighting well enough, that theta there would be the same value down here. So if the magnitudes are the same and the angles are the same, then the scalar projection would also be the same. So if we see in this triangle, you've got a right angle. So we have a right angle there, we have theta there, and we have that hypotenuse length that would be the same as my magnitude of B down here, also with a right angle and the same angle theta, that base of that triangle in both cases would have to be the same. So that would be my explanation for C. Because the two angles and magnitudes are equal, the triangles formed are congruent. Or you could be more specific and say that the scalar projection of A on C is A dot C times or divided by the magnitude of A, and that B dot C divided by the magnitude of B would have to be the same because those thetas are equal. So the scalar projection would be the magnitude of A times cos theta is equal to the magnitude of B times cos theta. So that's the calculations you would be looking at. For D, does the vector projection of A on C equal the vector projection of B on C? And that will as well, because the direction, A and B are just kind of on opposite sides, but that will also equal. So remember that the vector projection would be the A dot C over the magnitude of A squared times vector C, which would equal the magnitude of A times the magnitude of C that would be C on the bottom. Cos theta over the magnitude of C squared times vector C. So we would have those vector C magnitudes canceling out, and we would know that that would also equal the magnitude of B times cos theta over the magnitude of C. So if the magnitude of A and the magnitude of B are equal and those angles are equal, we would have the same thing there. Okay, so 15A is a nice little proof. So remember that we knew cos alpha was x over the magnitude of OP, and cos beta is y over the magnitude of OP, and cos gamma is z over the magnitude of OP. So here, the left side, we've got cos squared alpha plus cos squared beta plus cos squared gamma. So that's going to be x over the magnitude of OP squared. Put this, I might square both of these things individually, and then y squared over the magnitude of OP squared plus z squared over the magnitude of OP squared. So here we get x squared plus y squared plus z squared, and remember that the magnitude of OP is the square root of x squared plus y squared plus z squared, but then that whole thing is squared, which will cancel out with the square root. Which equals 1, and that is equal to the right-hand side. Then I'm actually going to add a slide in here to get myself a bit more space. So here we're looking at what are the coordinates of vector OP that make an angle of 30 degrees with the y-axis, 60 degrees with the z-axis, and 90 degrees with the x-axis. So we are not going to have a single answer here. Remember that this vector that makes these certain angles could be any magnitude, and it could be kind of any scalar multiple of it, but we're looking for a vector, so one particular vector that we could find. So 30 with the y, 60 with the z, and 90 with the x. And 60 degrees with the z-axis and 90 degrees with the x-axis. So first of all, remembering our special triangles, cos 30 would be, that's the 1, 2, root 3, so that's going to be root 3 over 2. Cos 60 is 1/2. And cos 90 is going to be equal to 0. So remembering the formulas from before, I know that cos alpha is x over the magnitude of OP. So here, this is alpha. We're in kind of an awkward order here. Alpha, beta, and gamma. So cos alpha is x over OP. So 0 is equal to x over the magnitude of OP. So x would have to equal 0. I know I'm going to have my x component equal to 0. And then cos beta is equal to y over the magnitude of OP. So root 3 over 2 will equal y over the magnitude of OP. And then similarly with gamma, now we could have any scalar multiple here with any magnitude. So I'm just going to say let the magnitude of OP equal 1. Just let this be a unit vector, just kind of for simplicity's sake. And then that will make the calculations easier. So then y is going to equal root 3 over 2, and z is going to be 1/2. So those would be the components of a vector that would make these angles. So a vector remember there could be any scalar multiple that would still work, would be 0, root 3 over 2, and 1/2. People may choose to multiply that vector by 2. That won't change the angles. It'll just make it longer and eliminate those fractions. So you might also have 0, root 3, and 1. So the magnitude being equal to 1 is pretty arbitrary. It's just kind of to make the math a bit nicer when solving. So the last part, I'm going to have to add another slide here for C, says that in general, the direction angles don't always add to 180. Often they don't. So alpha plus beta plus gamma are not typically equal to 180. What happened here that they were? So how did these angles add up to 180? Because we do have a sum of 180 here. And this might be easier to visualize if you actually kind of like pull out some pens or try and make a three-dimensional box and like hold up some pens or pencils to be your vectors. But I'm going to try and draw it out here for you as well for part C. And the answer here is that if we have one of those angles being a 90 degrees, so if we have a vector that's, say, on the XY plane, or on the YZ, or on the XZ, if one angle is 90 degrees, so this one here would happen to be gamma, then the angles for alpha and beta, then they would fall in a 90 degree section here. And this is actually not drawn too well because this is actually going to cause a negative angle, which will sort of mess things up. But it's harder to draw it projecting out into the positive direction. So maybe you'll just kind of like excuse that part of this. But what we want is two components that would be positive, so that these would make an acute angle with the positive y and z, for instance. Or another vector I might draw like, for instance, going up here, that this would have some kind of angle. If this one, it is very hard to draw in 3 dimensions. If this vector here was flat on the y and z, then it would form a right angle with the x, and then these two angles here would have to add up to 90. So the condition would be that one component is 0. So the vector is on the xy or yz or xz plane. And the other components would have to be positive. So that they would make 2 angles inside that right angle that would add up to 90, and the vector that it was not on that plane, the other axis would be perpendicular to that plane, so it would be a 90 as well. Just like in this past example, this vector is on the YZ plane because our x component is 0, so we get a 90 degree with the x-axis, and the other 2 would add up to 90 as well. So 90 and 90 is 180. A vector in R3 makes equal angles with the coordinate axes. Determine the size of each of these angles if they are A, acute, or B, obtuse. So here, we could say that cos alpha would equal cos beta, which would also equal cos gamma. So we would have x over the magnitude of OP would equal y over the magnitude of OP, which would equal z over the magnitude of OP. So we know that the denominators are all equal, so that would have x equals y equals z. So then we could let the vector be, for instance, 1, 1, 1. You could have it be 2, 2, 2, 3, 3, 3. It doesn't matter as long as your x and y and z components are all equal. So in this case, this would make acute angles because it's going in the positive direction to each of the x, y, and z axes. Then you would just be able to figure out, find the magnitude of OP, find the angles. I'm not going to go through all of them, but once you have the vector, figuring out the alpha, beta, and gamma should be pretty straightforward. The next one says obtuse. So it's going to be a similar argument here. So we'd have x over the magnitude of OP would equal y over the magnitude of OP, which would also equal z over the magnitude of OP. But remember, if theta, so if we have an obtuse angle, so that's between 90 and 180, cos theta is negative. So thinking about the cast rule or thinking about the graph of the cosine function, after 90 and till 180, you have negative values there. So that would mean that we know the magnitude has to be positive, but here x, y, and z would all be negative. So we still have x equals y equals z, but they have to be negative values. So let's let the vector be -1, -1, -1. And you can figure out what those angles would have to be for that vector. So here you're again going to find the magnitude and use that in the individual components to find each of those angles. They should all be the same. And I think that that's it for today's homework. Please continue to add questions to the Jamboard, and I will take them up or make videos.